things about the plan. So first of all, if you remember nothing else from this talk, the whole point is just to try to get across this idea that these symplectic singularities, so something coming from algebraic geometry, give rise to many what I think of as interesting examples of hyperplane arrangements. Okay, so if you're looking for new arrangements, you want some machine that you can just feed in something to get arrangements out, and symplectic singularity is the one way to do this. The other thing is that, even if you give a mediocre talk, you should stick to the basic idea that the first 15 minutes is for everyone, the next 15 is for the experts, and the last 15 is for that person on the back row on the third seat who, the other person who understands everything.
He's in the front row.
So I'm going to break even this mediocre rule. So my first part is going to be the technical part that everyone will get lost on. And then after that, it gets much easier, and it's just nice examples. So you can see for the first half, you wake up for the second half. Okay.
That's fun.
So I should tell you the things that we're interested in. So these are things called conic symplectic singularities. And I'm afraid I'm just going to throw the definition at you. So everything is over complex numbers. These are affine varieties. And they just have to satisfy these four properties. So I guess normality is just a technicality. You want everything to be well behaved. Somehow this is the key thing. So generically, it's looking like a symplectic manifold. It has a symplectic form on the smooth locus. And then this is technicality saying that somehow this form on the smooth locus has to somehow behave well as it degenerates towards singularities. And the way this is encoded is to say that if I resolve the singularities, then when I pull back this two form, that's really only defined on the open part of Y where this is a bijection. And so you ask that actually extends to everywhere on Y. This is a regular form, so it has no poles on the exceptional locus. And then fourthly is this extra word conic. So conic just means that if I look at functions on my variety, this is an n-graded algebra and it's connected. So degree 0 is just the complex numbers. And I want my form to have strictly positive weight. Okay, so somehow the idea here is that everything is contracted down to this most singular point, really. Or in other words, it's a way to extend formal statements about the most singular point to the whole space. Okay, so those are the varieties we're interested in. And there's a technicality in this part 3. So I said that you want this to extend to a regular two form on the whole variety. Now, that's not the same as saying it's a non-degenerate two form, right? So saying it's regular means that this thing has no poles. But you really want it to be symplectic, so you want it to have no zeros as well. And so in those cases where it has no zeros, it's actually a symplectic form on Y. And so we say that this resolution then is a symplectic resolution in that case. And just another comment. So there are many examples of conic symplectic singularities. Symplectic resolutions are much rarer. Right. So of course, here's the standard example. If I just take a Kleinian singularity, then this is a conic symplectic singularity, and the minimal resolution gives you a symplectic resolution in this case. And I'm going to assume throughout that there exists some symplectic resolution. They have to be projective, be technical. And there's also hidden in here a very big lie. So, like I said, these symplectic resolutions are very rare. And you'll see that throughout the rest of the talk, I'm always going to assume they exist, which in general they don't. But the point is that there's a good substitute. So there's something called a Q factorial terminalization, and that at least always exists. So really, when I'm saying a symplectic resolution, I mean this other thing. But I don't want to sort of bore you with the details of what that thing actually is. But the point is they always exist. And so you can just pretend that they're symplectic resolutions. Okay, so we want some hyperplanes. So I better give you a space. So what we're going to do is we're just going to take a second cohomology of this symplectic resolution. So that's going to give us a real vector space, and it has a natural Q form, which is just given by the rational cohomology. And so our hyperplane arrangements are going to live inside this H dual. Okay, so the first big theorem in this area is this result by BCHM, sorry. So first of all, it's a sort of miracle that this X only admits finitely many symplectic resolutions. Okay, so in particular, it makes sense to ask how many symplectic resolutions these conic symplectic singularities have. And the second thing is that inside my H star, there are two, well, there are many, sorry, there are these natural polyhedral cones. So there's something called the movable cone, and then that's tiled by these things called the ample cones. So ample cone, you probably know, they're the cones spanned by the ample line bundles on your variety. Movable is a bit more technical, but you can take this as a definition if you want, that it's just covered by these finitely many polyhedral cones. Okay. So this we know by this huge theorem always exists.
Sorry, they're just polyhedral, they're not necessarily simplicial, presumably.
No, they're not counting that.
Are they rational?
Are they, sorry?
Rational.
They are rational, yes. Yes, we'll see, yeah.
Homology is independent on the resolution, right? So
It is, yes, that's a good point. So you notice here, I mean, this is somehow, for me, the miracle in this statement is that I fix one resolution and yet it sees all the resolutions. And this is precisely because of Pavel's point that the cohomology is independent. And this is because all these different resolutions are isomorphic in codimension 1. And this cohomology only depends on that. Yeah. Okay, so the previous,
actually all cohomology groups are independent. Not just H2.
yes, that's true, actually, yes. I'm not sure I could justify that, but yes. Okay, so the previous statement is true in some great generality in rational geometry. This one is far more specific to these conic symplectic singularities. Okay, so the claim is there's some finite hyperplane arrangement, rational, inside H star, which contains a Coxeter subarrangement, which has the property that, first of all, this movable cone is a fundamental domain for the corresponding action of the Weyl group. This Weyl group preserves this larger hyperplane arrangement. And these ample cones you get by taking the movable cone, so this fundamental domain for the action of W, and just removing every hyperplane arrangement. And maybe just to emphasize, now this is very specific to these conic symplectic singularities. In general, when one looks at well, singular affine varieties and does these resolutions, often you get pictures that look a bit like this, right? So this is a picture where the movable cone is everything, and it's divided into 3 ample cones. We see in this case, this statement C is false then, because I cannot extend these to give 3 hyperplanes that define this picture. Okay, so it's very special that this decomposition is given by hyperplanes for these constants. So the upshot is simply that for any of these conic symplectic singularities, you get naturally a vector space with this pair arrangement, right? It's an arrangement with a Coxeter subarrangement. Oh, and this W is called Namikawa Weyl group. And it's a genuine Weyl group, so it's not just some arbitrary Coxeter group.
Because it preserves the integral cohomology.
Well, that's very right. Yes, that's yes. But it also comes from foldings of ADEs, which also only give you Weyl group.
But it has to be crystallographic because it preserves.
Yes, that's good. Right. Yeah. Okay, so like I said, so one thing that the algebraic geometers are interested in is to understand all the symplectic resolutions, and I guess the first thing we're going to do is to count them. So in particular, you see many papers looking at these things where this quantity is studied in general. But of course, it's very hard to work out examples. Okay, so that's just that again. Right, so that was the hard part.
Is complement.
Oh, sorry, yes, yeah. Just trying to pretend to be an expert. Yes, this seems to be the notation for complement of the hyperplane. I should have said that. Yeah. Right, so that's all the hard parts. So now, from now on, it's literally just going to be examples, many examples. Okay, so we go back to the first example we had. If we just take Clanyon singularity, then of course there's naturally a Weyl group and a Cartan space associated with the Mackay correspondence, and this is what you get when you run this machinery. So nothing new there. That only gives you, of course, ADE Weyl group. So you can ask, well, what about the other Weyl groups? And one way you can realize those is to look at the nilpotent current for the corresponding simple Lie algebra. That's a symplectic singularity. It has a canonical resolution, which is the Springer resolution. And you notice this is a cotangent bundle, so it's symplectic. So that tells you this is a symplectic resolution. And again, when you run this whole machine, well, it goes back to more classical results, I guess, but what you get back is just the Weyl group for that algebra and the Coxeter arrangement. Now you notice in both of these cases, the Coxeter arrangement is the same as this larger arrangement. You don't get any extra hyperplanes. And oh, I guess I didn't say that. But, in that formula I write down, what is that doing? It's really counting for you. So if this is my Coxeter arrangement, then you add in some extra hyperplanes. And what you want to do is you want to take your fundamental domain and you want to count how many additional chambers I have in that fundamental domain. Now, in this case, the Coxeter arrangement is the larger arrangement as well. So there are no additional hyperplanes here. So how many chambers do I have here? Well, it's just one. Okay, and so what that fact is really telling you is in these cases, in both of those, there's a unique symplectic resolution. Okay, because there's only one chamber within the fundamental domain. Okay, so that looks in some sense slightly boring. There's nothing new or interesting going on. So now we'll go to maybe my favorite examples. So complex reflection groups. Okay, so that gives us many new examples. So you take your favorite complex reflection group. So I'll write S for the set of reflections. So you want something which is symplectic. So what the trick we do is we double up. We take V times its dual, you know, in some sense, just as we saw in the last talk.
So I have a question. So this number, homology of M of A, is this a number of components of the complement in the real space?
Yes. So I'm not quite sure. I'll say again, sorry.
Well, you take the real space,
Yes.
the real arrangement, right? So
Yes.
take the real space, delete the mirrors, then you get certain number of components. Is that the number of
Yeah.
components?
Yes.
So divided by order of the value.
Yes, because
That's freely on the components, so it's number of orbit.
exactly, yeah. Because you see in this picture, right? We want to know how many are here. Right, you tile the whole thing and then you just divide by them. Yeah. Okay, so in this case, I mean, this is, I apologize, it's very confusing, right? I have a complex reflection group, then I have a H star, right? This H star is not the, of course, the representation of the complex reflection group. It's something completely different, which is quite unrelated. So the dimension of this thing is the number of conjugacy classes of reflections in your complex reflection group. And so this is, well, I see a much more general statement by Ito and Reed. And then we computed, so in this case, the Weyl group you get is simply a product of symmetric groups. Right, to tell you this notation. So usually this would be an A, but since I have an A already, I didn't want to use that. So this is the set of reflecting hyperplanes in your complex reflection group. You look at orbits of those reflecting hyperplanes, and then you just take the order of the stabilizing subgroup for one of those things. So for instance, if you start with a Coxeter group, this is just
Two. Yeah, but it could be higher, right?
general.
I think.
So this is what I call E in my book.
Yes, H is E. Yes, that's a good point, right? Yes. Okay, so some examples. So this is a particular favorite of mine, you know, because everyone knows this G4, this is the smallest of the exceptional complex reflection groups. And probably most of you already will guess from part C that here you just get the symmetric group on 3 letters. And H is just the reflection represent, or H dual is the reflection representation. So when you make this computation, what you'll find is you get 6 hyperplane arrangements. And so the computer will tell you this is 12. And so if you divide the order of W, 12 divided by 6 gives you 2. Okay, so in this case, there are 2 symplectic resolutions.
If there were no resolutions, you would get, this would count terminalizations.
Okay. Yes. Yeah.
Can I ask for the case of SN? What happens specifically? What happens for gamma equals
Oh.
SN?
Well, in this case, this gives you 2. That can't be. So there's only 1 symplectic resolution. So in the end, the number is 1.
Just one order.
Yeah. So yes. Well, actually, in this the symmetric group is rather boring. Sorry. For this reason, right? You know that there's only 1 conjugacy class of reflections. So that tells you that H star is 1-dimensional.
Oh, okay,
So you have this arrangement, which is, well, the only arrangement you can get.
okay,
And
Still.
order 2.
okay, thank you.
It's 2 divided by 2. Yeah, that's good.
And when you always get, I mean, if there is a resolution, will all these terminalizations be resolutions?
They'll all be smooth then. So as soon as one of them is smooth, they're all smooth. That's a result by follow some Namikawa's.
So what is this polyhedral complex in this situation for G4? You had a polyhedral MOV of MOV
Oh.
or something?
Well, so inside here, you've got the Coxeter arrangement. Somewhere. So some of these will give you the Coxeter arrangement. And you just want to take the fundamental chamber for that and cut out. But well, I don't know, I can make more precisely than that. So well, it'll be this one, actually, precisely this one. And then you add in an additional
1. Yeah.
1 hyperplane, yes, and it's sort of translates. So you take the A2 Coxeter arrangement, you throw in this 1 extra 1, it's this in 2, and it translates.
And so what happens in those hyperplanes algebra geometrically? So
Well, they're partial resolutions as you hit those. So they're singular, but they're not as singular. So I can tell you, so along these walls, as you go from smooth to the wall, these are external walls, these are divisorial contractions. They're on the Coxeter hyperplane. This one is special. This is going to be a small contraction.
and so if you consider the corresponding unique algebra with 0 one constant, then center is going to be more singular along these lines. Yes.
Yes, exactly. And it tells you the,
In particular, in this case, is exactly the lines where the center isn't smooth.
yes, but it tells you the codimension of the thing. So here it's going to be singular in codimension 2. Here it's going to be singular in higher codimension. So in this case, it's going to have an isolated singularity, actually, in this particular example. Because it's
On the additional hyperplane is singular in codimension 4.
yeah. Yep. Okay, so here's some more examples to go quickly. At the time we wrote this paper about 6 or 7 years ago, this was the state of the art. So Thiel is an expert on doing massive computer computations, so maybe we know more by now, but this is only what we knew about the exceptional groups at that time. So this is the number of hyperplanes in the arrangement. Yeah, well, that's the Weil group. And so actually only G4 admits symplectic resolution. So none of these admit symplectic resolutions. These are counting these more general Q factorial. And as you can see, for some groups, you have many, many different resolutions.
Is the Weil group always a subgroup in a natural way of the group? Or the Weil group of the,
Oh, is that true?
no, it's from
no,
natural,
no, no.
It has nothing to do.
It has nothing to do with.
No.
I mean, what you get is the cyclic group corresponding to the symmetric group is a
Yeah.
minimal stabilizer subgroup.
S3 is generated by involutions, but G4 not.
No, they're not really.
No. Not in the group.
Can you repeat again how to compute the codimension of singularity locals on the hyperplane?
Well, it's right. So somehow abstract theory tells you what the code, well, that these have to be code dimension 2 and these have to be higher code dimension. So we don't actually compute those. We just compute whether it's smooth or not.
But
Well, in fact, in this case, you can't even do that because there's always singular.
but it is hard to confuse.
Yes, well, I'll tell, okay, maybe just for Pavel, I'll tell you. It's extremely indirect. So in reality, what we do is we compute the blocks of the restricted rational quadratic algebra and see how they vary as you vary C. And they degenerate along hyperplanes. So these are the Clodromosa families for that thing. And then you have to prove that that's the same as these other geometric. arrangements. So it's extremely indirect. Yeah, okay, so there's some numbers. So this is a slightly different case. This is leaving the world of complex reflection groups, but there's still quotient singularities. So I take a Kleinian singularity again, and I somehow extend it to higher dimensions by taking a semi-direct product with a symmetric group. So I take n copies of my Kleinian group, and then I can form this quotient variety. And so in this case, it sort of generalizes what happens with Kleinian singularities. So when n is at least 2, you get an extra copy of R appearing in your Cartan space. This is just the Cartan space for Weyl group associated to gamma. Your bigger group is not much bigger. You just have a copy of Z mod 2 appearing. This is somehow corresponding to the symmetric group part. But the arrangement becomes more interesting. So this is what's called extended Catalan arrangement. So this seems to be a well-studied arrangement in, well, in theory, hyperplane arrangements. And so there's this amazing result by Athanagiadis, who gives you a very explicit formula in this case for this number of resolutions, just in terms of, so H is the Coxeter number and the DIs are the degrees. Polynomials. And so in this case, we actually constructed all the symplectic resolutions explicitly because they're just given by Nakajima equivalent varieties. Okay, so somehow this is a much more non-trivial example. This is the final so quotient singularity example. It's a sort of baby example, but I put it in for 2 reasons. So one is that it's going to reappear later. And the other is this is actually very special. So there are only 2 exceptional what are called symplectic reflection groups where the quotient emits a symplectic singularity. And this is what G4 is one, and this is the other one. So they're very rare. And Travis Shedler and I discovered this one many years ago. So it's just acting on a 4-dimensional space, Q8 and D8. So they're the 2 non-abelian groups of order 8. So the dihedral group and the quaternion group, they have a common center. And so you kill that common center. That's some group of order 32. And it turns out that this thing emits a symplectic resolution. And you just run through this whole game again, and you get these invariants coming out. So the Weyl group is just a product of S2s again. There's this unusual hyperplane arrangement appearing. And then finally you compute this number and you get 81.
Is it coincidence that this is a 3 to the 4th, or is there a structure of vector space over F3?
No, this seems to be some bizarre coincidence, actually. I'll come back to the numerology in a second, but maybe there's something there. I mean, to me, this was very strange, and I thought the computer made a mistake because this group is of order 32, right? So there's no 3s at all there. And yet this is only 3s. So I was very suspicious of this, but then it turned out that some algebraic geometers use toric geometry to compute explicitly the resolutions, and they counted 81. So when we exchanged emails, I was amazed to see this email come in with 81 in the title. I thought, wow, okay.
Not 42, it's 81.
Yes.
That computed it before, or
At the same time, as it, yeah.
did they go looking for it after you told them you found 81?
Oh, I see. Well, there's a bit of sort of disconnect. So we found this many years ago, but at that time we didn't actually compute how many resolutions. So it's only some years later that I wrote another paper about counting resolutions, and I came up with this 81. And I mean, well, just after I put that on the archive, they got in touch to say, oh, actually, we're about to have submit this paper where they explicitly computed these resolutions and got 81. Using completely different methods.
And so is it true that, oh, okay, so you have this deformation also over this age? And so then, is it true that when you degenerate this deformation into resolutions, then when your deformation parameter is in the appropriate chamber, then it goes to the resolution corresponding to this chamber. And when it is on the
well-
boundary, then it goes to something more degenerate.
You have to be careful. So, I mean, the point is you take a resolution and your singularity, you deform the pair. So your statement is
So
true.
the whole family, try to
Yeah.
degenerate the whole family.
Yeah.
And then is it true that when you degenerate, then you have these chambers, and if you are in that chamber and you degenerate, then it will degenerate to the resolution that combinatorially corresponds to the chamber.
No, actually, really. So how to see this? Well, okay, so in the Kleinian singularity case, there's only one chamber for the resolution. And yet in the deformation, you've got many chambers.
Yeah, but okay, there are orbits. So if they are related by the Y group, they will be the same. But
Yes.
so there is a bijection between resolutions and orbits of chambers, right?
That's true. Yeah, yeah. But
Not only the same number, but there is actually a bijection.
yeah, there's actually, yes.
And is it true that when you go to the limit in the chamber, then you get the corresponding resolution? That was my question.
No. Bizarre. So, I mean, the point is, so somehow the deformation space and the resolution space are the same, but they appear in different ways. So you cannot, I mean, the point is you can always degenerate to anywhere in the deformation space, starting from a fixed resolution. So your statement can't be true then. We can talk about this afterwards, but yeah, it doesn't quite work like that.
Sorry, can I ask a last question? The subset you index over, is it was fixed one or all
Oh,
subsets?
sorry,
are
that's a good point.
complement?
Yeah, I didn't explain this, sorry. So this is, you take all subsets of 5.
Yeah.
And then you
Do
do
this,
this.
okay.
Well, non-zero subsets. No. Yeah, thank you. Okay, so that's the end of the quotient singularities. Now we move on to a completely different space. There are these spaces, a moduli space is called hyperpolygon spaces. So a polygon space, I'll say it very quickly, is literally parameterizing polygons in R3. So a polygon in R3 is you start at the origin, you go some distance, then you go another distance, then a distance, and then you eventually get back. And you can ask up to rotational symmetries of R3 to describe all possible polygons. And this gives you the polygon space. So that's a Kähler manifold, and hyperpolygon spaces are just do that construction, but in a hyper-Kähler way. And so from our point of view, what you get is a quiver variety associated to this star-shaped quiver with these dimension vectors. So I just assign 1 to every external vertex and a 2 in the middle. So it doesn't really matter, where these come from, but it gives you examples of conic symplectic singularities. And so you can do the same game again. But this time it's a Hamiltonian reduction. So you now have a connected reductive group acting instead of a finite group. And so you do this Hamiltonian reduction and you get an example of a quiver variety of a given dimension.
Use the moment map or use the.
Mu is, yeah, sorry, I should say, oh, I didn't say, yeah, so mu is the moment map for this Hamiltonian action.
So you want n greater or equal to 4?
Yes, otherwise it doesn't make sense.
So for 4, you get the D4 singularity, and for 5,
Yes.
you get this, okay.
So we were interested because Ryan made this, well, it seemed like slightly crazy conjecture, but it turns out this quotient singularity that Klaus and I studied many years ago can actually be realized as somehow the first non-trivial hyperpolygon space. So we became interested in it because of that. But
What about G4? Is it realizable?
no, well, yes, it's realized as a Hamiltonian reduction, but by a quotient by SL3. So you don't get any of the deformations or resolutions. And I don't know how to do it.
So all resolutions known, all known symplectic resolutions
well, at least the quotients can be realized as
The resolutions are obtained by reduction.
the resolutions is not known then for G4. Or we can do it in such a way that GIT gives you the resolution. The example I gave, the quotient by SL3, so there are no non-trivial characters for which you can do GIT. Okay, so that's why I mentioned this previous quotient. Yeah, this is a very repetitive talk, sorry. So you do the whole thing again, and this time this is what you get. Okay, so it's the same pattern of arrangements. You take I to be some subset of 1 to n, and you get this unusual arrangement. Doesn't seem to be in the literature. Well, yeah, we haven't seen it anywhere. So as Pavel mentioned, if you do n equal to 4, right, you just get the D4 quiver. So you know, and with the minimal imaginary root as your dimension vector, so you know that you just get the quotient singularity. And sorry, the Kleinian singularity. And so there's only one resolution in that case. You get 81, as I mentioned before, for that case. I asked the computer, and eventually it told me you get that many for n equals 6. But this is very recent, so I've just been told this. So Hubbard, who's a student of Craw, somehow managed to compute n equal to 7. I have no idea how he managed to do it, but he got this big number out. And then Alistair King got very interested, and so he's noticed that this sequence of numbers is actually counting something combinatorial. And
What was it in the online encyclopedia?
yes, so that's a good point, right? So if you plug this sequence in, the online encyclopedia will tell you it doesn't recognize it. And the reason it doesn't is because this number is incorrect inside the encyclopedia, it seems. So there's a different number that if you plug that number in and you plug the whole sequence in, it'll tell you, oh yes, I know this sequence.
But if you plug sequence without this number, then it
Yes, well you can do
1684 will recognize it.
yes. Oh, well, yes and no. See, I think this is, well, I guess
Do you mean n1 equal 1 or n4 equal 1?
yeah, see, this is right. So precisely. So if you plug this in, and I think this is what we did when we did this paper, it doesn't give you anything. But as you pointed out, that sequence is not this sequence. And the reason for that is a technicality. So for n equal to 4, the Weyl group for the D4 Kleinian singularity is the D4 Weyl group. It's not S2 to the 4. And so something bizarre happens in the geometry there. The Weyl group is bigger than it should be. So if you literally take this as your definition and work out these numbers, you get this sequence which is recognized. But actually the geometry tells you that for n equal to 4, the group is incorrect. So this is why I put the 5 there. Right, so that statement is correct with the 5. So it's some strange, somehow the geometry doesn't quite behave the way it should do for these small numbers. Strange. Okay, I can't answer any questions on this. I tried to find even the definition of this thing, and I just cannot find it. So apparently it's counting something to do with Boolean algebra. So I guess the computer scientists know it. The number of self-dual threshold functions. And King apparently can prove that this sequence really is this counting these complements to the hyperplane arrangement. So yeah.
Alistair King?
Alistair King.
Alistair King.
So this is a theorem. No.
Apparently, yes, but I only know this secondhand from Craw, so I've not seen anything written down. But I'm sure if King says he can prove it.
King and Bath.
Okay. Right, so somehow in my mind, these are the most non-trivial examples. So if you take a general quiver, Nakajima quiver variety, so I'm afraid I'm not going to tell you what that is, but the ingredients is you just take a finite quiver, you pick some dimension vector for that quiver, and then from this one gets one of these conic symplectic singularities. And also, when you do your representation theory of quivers, and so you know that associated to that quiver is some infinite, or generally infinite root system. Okay. And so, I mean, this is not written down any. Oh, actually, it is that. Sorry, yes. So this is an amazing theorem. I'll tell you why it's an amazing theorem, because I am not going to define this set. So I'm saying, provided something is satisfied, then all sorts of things work.
Then it's true.
So you'll have to take my word for it. You can always reduce to some alpha and sigma. And maybe for the experts, it's just to say, that's a condition that there exists a simple representation of your pre-projective algebra of that dimension vector. So when you're in that situation, it turns out this H star is what you expect it to be. So it's just the set of all characters of your product of GLNs that pair to 0 with your dimension vector. Probably more unusual is this alpha. So, this is generally an infinite set of positive roots. You take all those roots such that it and alpha take away it, positive. So that's some finite subset. And that gives you the hyperplane arrangement for these group varieties.
So these are real roots of some Kac-Moody algebra.
They could be imaginary. In general, they will be imaginary actually also. So real or imaginary. And they're not for a Eric Vazaro called me up with this. I mean, for a general quiver variety, there's no Kac-Moody algebra associated to it, right? It's just defined in terms of the quiver.
Well, if there is no self loops, then
Yeah, but this works. With loops, and somehow that's a more interesting
if
case.
there is no self loops, then it is.
Then it is, yes. I don't actually know when I meant to stop. My overtime already.
We have 7 more minutes, including questions.
Oh, right, okay. Good. Okay, so one thing which is missing in this statement is the description of the corresponding vial group. Right, so inside here, there is some Coxeter subarrangement. It seems to be very difficult to work out what this is. So there's a student at Losev who has some partial results on this, but nothing concrete that I can say. So yeah, to my mind, this is somehow the most non-trivial situation.
So when Crowley-Bowie has this paper about the Lin-Simpson problem and the interpret terms of and he has conditions of splitting a root into a sum of roots.
Well, that's also how you define this set sigma. So there's a certain quadratic function whose value on alpha has to be strictly greater than its value on any decomposition into smaller roots.
And this definition A is like, it sounds like we're splitting alpha into a sum of 2 elements of R plus.
Yeah.
Is it kind of similar to what he's doing?
Yes, it is. Well, in fact, that's precisely, yes. So this is where these claims come from, is that this is generically, well, this allows you to say that for generic theta, you're stable, every representation is stable. Now you can say, what's the simplest way you can stop that from happening is when you degenerate into a sum of 2 strictly, well, you're polystable, but you're a sum of just 2 stable representations. And the non-trivial part is to say that actually that's precisely what happens on the hyperplanes. So the simplest degeneration is the only, well, not the only thing, but that defines for you the hyperplanes. Okay, so there's one other class I wanted to mention just because the hyperplane arrangement you get seems to be very general. So from the geometric point of view, these are the simplest examples you can really look at. So this is where you do Hamiltonian reduction for a torus. So I just take a rank R torus acting on Cn. So to encode that action, what I need is I just need to encode the weights of each sort of coordinate vector here. And that's encoded by a matrix, an integer valued matrix. And the theory to be nice so that the statements are clean, you need to assume it's unimodular. So it just tells you that every R by R determinant is plus or minus 1 or 0. So that allows you to fit your A into some short exact sequence. And when you do the Hamiltonian reduction, you get some conic symplectic singularity, which has been very well studied by now. Okay. So I think probably partial results in this direction will be written down in many papers, but the conclusive one is by Nagaoka. And so what they proved is that if you look at this B and you rearrange the columns so that the first L1 columns are the same, the second L2 columns are the same, and so forth, And you can always make this assumption. Then what you get is that the hyperplane, sorry, the space is just the space you expect. Your Weyl group is just the product of these symmetric groups. And then your hyperplane arrangement is you just look at all these weights that describe the action, and you take all subsets that generate a subspace of codimension 1. So that gives you some general hyperplane arrangement. So I guess I just wanted to mention this example because it is quite a general hyperplane arrangement that one can get in this way. It's a very combinatorial thing. Okay, so that was all the examples. And I'll just finish with the sort of very obvious 3 questions coming from this. So the first one is how general really is this construction, right? If you give me an arbitrary arrangement with a Coxeter subarrangement, does there always exist a conic symplectic singularity that realizes this? I mean, based on the hypertoric one, it wouldn't surprise me, but I don't know how one would construct them either.
Yeah, just but Namikawa shows that there are countably many symplectic singularities. So
That's true. So would that rule it? But
what would that
these
be?
are rational arrangements.
Are rational.
Yes, all arrangements are rational. So is that not also countable? Well, yes, it seems like. I don't know. I guess
There are finitely many was given numbers of the resolution. I don't.
well, I think
There is some theorem of this sort.
yes, but he bounds the degrees. So he says that if you have a, I think, if I remember correctly, if you have a conic singularity generated by things in degree at most 5, say, then there's a countable family. Something like that. Yeah, so I'm not sure. Maybe this is just wishful thinking. That's one question. Another one that certainly the algebraic geometers would be very interested in is to sort of have effective ways to compute this n, right? So they really want to describe the resolutions, and so compute this n. And the third thing to comment about, which has been mentioned in previous talks, is of course this naturally gives you a Weyl group action on some cohomology of some hyperplane arrangement, and so you can ask the expected question: what does this? I have no idea.
Which is the same as to ask how many points over a finite field it has, yeah?
Well, I'm not an expert. How does that take into account the W action?
Together with the W.
Together with the W action.
How many orbits of W over
Well,
finite?
just in degree 1 then. It's not, it's the total space you're looking at. You have higher,
But if you just take a complement over finite field and consider action of W and look count orbits, won't you get this one? No. No?
No, it's related. I mean,
No, it's related.
Blair has some results about relating that. Those two things.
It's work of Egedal and Jordan.
You can compute one from the other, or
I remember what the relation is.
Okay, so that's